So neural networks are great for learning lots of types of complicated functions. I mentioned last time that neural networks were kind of the thing that really took off in the field of image recognition over the past 10 years or so. So let's talk a little bit about how you might train a neural network on image data. So you might have an image, and an image is, as I kind of mentioned before, is really just a grid of pixels. So it's a big matrix. One individual image is a big matrix of pixel values. And that corresponds to how your monitor shows you pictures. It's actually a big grid of tiny, tiny pixels that turn on to certain colors based on whatever the image says to be at that location. So the most straightforward approach of trying to learn something with images is to flatten the image. This is the simplest kind of representation you can imagine for how to put images in an ML system. Note, we talked about this before. Pretty much every machine learning algorithm we talked about so far, every ML model, just assumes you have a vector of numbers. So really, any kind of way of trying to transform data into that vector of numbers can work. And the simplest one is just keep all the pixels, but then flatten them into one long image. That's going to have height times weight pixels in it. Now, one thing to note is that how images are represented in this kind of grid of pixels is that each pixel actually represents more than one value. So instead of having one number at each pixel value, there's actually three. This is because our screens show us things in an RGB space. RGB for red, green, blue. What that means is that each pixel specifies how much red, how much green, and how much blue should be shown at that one tiny pixel value. And that combination of red, green, blue gives us every visible color on the computer. And you've actually maybe seen this before if you ever used a color picker or like a Microsoft Paint. They show you usually sliders of how much red, how much green, how much blue you want, and that can give you almost any color you want in Microsoft Paint. So when we think about images, they're not just a height by width, but they also have three channels. So I'm going to say three channels of this. Each channel is a height by width grid of numbers, and it's going to show you how much red is at each image in each pixel of the image. The next channel is going to show you how much green, and the next channel is going to be how much blue. So in some sense, one image is actually three images stacked on top of each other. Each individual subimage or channel is just precisely telling it at every location in the image how much red, or how much green, or how much blue, depending on which channel you're talking about. So really, we would have, for an RGB image, three channels at height times width. And we'll just use this. Oh, I meant that to be an @ sign. This is just the common notation to use an @ sign here to say the number of channels, to just make it clear that it's not like a dimension of the image in some sense. It's really just we have these three images stacked on each other. So if you have a 10 by 10 image, a very small image, 10 pixels by 10 pixels, if you were to flatten it, you'd have 10 times 10, or 100, times 3 for each color channel. So you'd have 300 pixels in total, or values for your image in total, which then we could use as our input layer for a neural network. And then we could maybe have a hidden layer and maybe an output layer. And then you can even draw it fully connected if you want, but I'm going to just kind of sketch this out. So my question to you is, I want to think about a particular data set called CFAR10. So CFAR10 is a very popular kind of image classification data set. It has a bunch of images that belong to one of 10 categories. Now, in CFAR10, you could imagine having very small images, 32 by 32 pixels, and they'll be RGB images. So they'll have 3 color channels. So we have 32 by 32 images. So 32 pixels, and then each one has 3 color channels, so we have 3 numbers in there. So if we were just going to make a neural network that worked on CFAR10 data with this kind of straightforward transformation of flattening, how many inputs would we have? Well, we would have 3 times 32 times 32 for a total of 3,072 input features. No, a 32 by 32 image is very, very small in the grand scheme of things. When you look at actual pictures, they might have thousands of pixels by thousands of pixels. Or maybe hundreds of pixels by thousands of pixels. And even with this tiny, tiny image, we already have 3,000 features that we're going to have to use as our inputs. Now, for moderate-sized images, this gets much, much worse. So you can imagine if you had images that were 200 pixels by 200 pixels, still RGB, so we have 3 color channels. So remember, this stands for our RGB. Then the number of inputs we'd have would be 3 times 200 times 200, which is about 120,000. That's a lot of input features. Remember when I was saying if you were trying to use neighbor-based approaches for things, we start falling apart around 30 or 40 dimensions of input features? Well, now we're at 120,000. That is so many inputs that we have to work with. And this gets worse when you start thinking about, well, for your hidden layer, you have to learn a completely different set of weights for each neuron in your hidden layer. So if you only have something like 4 neurons in your hidden layer, you're going to have to learn something like 4 times this number of inputs, 4 coefficients just for the first layer, because each neuron in your hidden layer is going to have a fully connected set of inputs to the input layer. So you're going to have this kind of blow up in coefficients you have to learn, or parameters you have to learn for even moderate sized networks, because you just have these relatively medium sized images. So what's really hurting us when we try to do machine learning or neural networks with images is usually this first layer. This one that has this fully connected layer from the inputs to your first hidden layer. And that's usually where kind of when you have image data and you have all of these inputs, things really start blowing up because there's just so many parameters that you have to learn in that region. So what we really want to try to take advantage of is that images are structured and that we should leverage this. Like maybe it's possible to have this notion of neurons looking at different areas of the image rather than the entire image overall. And maybe we could use that local structure of an image to help us make a better model overall. And so this enters the idea of a convolutional neural network. The idea is instead of having your hidden layer kind of fully connected to the inputs, you learn weights in a very local manner. You really focus on each area at a time. So what we'll do is we'll use this thing called a convolution to reduce the number of inputs by combining information in nearby pixels to one value. So instead of having this giant 200 by 200 image as our input, we'll use this thing called a convolution, which I'll explain. I'll walk us through what this means, to kind of go step by step and reduce, in some sense, the dimensionality of our input by kind of doing a computation on a group of pixels nearby each other in our input to make a new derived value based on that region. And there's lots of choices we have to make here about how we do that combination, how big of an area we look at each time, and we'll cover that. But the idea for a convolution is to have this kind of sliding window over our input image. So this blue image down here is our input image. And just for this small examples for today, it's a 4x4 image. And the output is the thing shown up here. This is our output image in some sense that's using a convolution. Now you can see what it's doing is it's looking at this dark blue region that's kind of scanning over the image. We sometimes call this a sliding window algorithm. It starts at the top left and kind of moves right and then down, and it keeps kind of scanning over the image, doing some computation to feed into the output. So we're going to have this sliding window kind of algorithm. Now let's talk about what type of computation it's doing. So what this convolution is doing, it's sliding across the image. It's using a thing that we'll call a kernel. And unfortunately, this is where terminology gets overloaded. Kernel has nothing necessarily to do with the kernels we talked about with like kernel regression. So this is not the same as that type of kernel necessarily, but we overuse or we reuse terminology sometimes. So we talk about kernels and convolution networks too. What we're going to do is we're going to slide a kernel of numbers. So I'll explain how this is set up. And we'll use a computation at each location of the kernel over the image to get something from our result. So as an example, I'll have this 5x5 input image that has numbers in it. For simplicity, we're just going to consider not colored images. So we'll just do black and white images. They'll only have one color channel about how black or how white each pixel will be. So that's another representation of images instead of RGB, is it's just black, white, or grayscale. And so we'll have this 2D array of numbers for the image. And the kernel will be some numbers that we'll come up with, and I'll explain how we come up with these numbers, that we'll use to combine at each location that overlaps with the image into something kind of smaller. We'll kind of, in some sense, compress that information using the kernel. So what we do is we start the kernel overlapping with the top left part of the image. So since the kernel has 3 numbers by 3 numbers, the overlapping region will be 3 by 3 as well. And then what we do is we're going to take an element-wise product and then sum them up. So what I mean by that is we're going to take each number in the kernel. I'm just going to write them down next to their spots in the image. So I'm just writing down the kernel values as they line up with the image. So these are the exact same numbers I'm writing down that's in the kernel on the right. What we do is we're going to kind of take this element-wise product. The element-wise product of these two things would be 0 times 3, which is 0, 3 times 1, which is 3, 2 times 2, which is 4, 0 times 2, which is 0, 0 times 2, which is 0, 1 times 0, which is 0, 3 times 0 is 0, 1 times 1 is 1, 2 times 2 is 4. We take this element-wise product, and then we're going to sum it up. And the sum of all these numbers, if you add them up, 3 plus 4 plus 1 plus 4, that's a total of 12. Then we'll use 12 as our result for this is what this kernel computed at this area of the image. So 12 will be in our output for this one position. So there are a couple key questions here. One is, what the heck is this computing? What do these kernel numbers represent? And what does this overall result represent? We'll try to tackle that in a second. But also kind of how this procedure works of doing this sliding. So I want to first talk about doing the sliding, and then I'll talk about how we try to interpret these and how these kernel numbers are decided. So we do this kind of kernel computation at each kind of feasible region in the picture. So we start with the top left, and this is the exact same image using the exact same kernel as before. Note, I'm using the same representation where I'm writing the kernel numbers in the bottom right of each cell. So we do this computation, element-wise product, and then sum to get the number 12. And now we're going to stick the number 12 in the top left position of our output. Ignore all the other numbers there for a second. Now that we've computed this kernel value at this one index, we now move on to the next index. So we move the kernel to the right, one position in the image, and do the exact same computation. Element-wise product, sum. If you do that here, you also get 12. Then, now that we're done, we stick the number 12 here. Then we move on to the next spot. We move it to the right one more. Element-wise product, sum. Turns out in this position, we get 17 as the answer, so we stick a 17 there. Now that we ran out of space to go to the right, we now go back to the far left side, but I'm sliding the wrong direction, sorry. That was me advancing the slides the wrong way. Then we go down to the left again, but down one row. Same computation, element-wise product and sum, move right, Same thing, move right, and then again, jump back to the left and move down one. And we just keep repeating this process over and over again. Note that our result here is in some sense like a smaller image. It has different values inside of it, but we've kind of combined the local information, this 5x5 image. Using this kernel, we ended up with 3x3. Note, there are no other kind of valid places to put this kernel because we've computed all possible places. We've slid it over. Anywhere else would have the kernel going outside the image. So you only have a 3x3 possible set of places to get this. So this will be our input, and this will be our output. So what does this output image actually represent? Well, it depends on what your kernel values are. Different settings of those kernel values generally find different numbers. And that, I think, is a pretty straightforward sentence. Like, if you use different numbers in your kernel, the computations you're doing at each step are wildly different, which means you get different values. It turns out that there are some special kernels, some special settings of those numbers that actually find you something useful about the image. So for example, if you use a set of kernel, or if you use a kernel where all of the numbers are 0 except the middle one being 1, it turns out that this is what we'd call the identity kernel, that the resulting image would look basically the same. So this is a famous example of showing some of these kernels. I believe this is called a vampire deer or something like that. It sounds kind of scary. But if you do this kind of computation, if you use my example from the last slide using this kernel, you would see that you'd get basically the exact same numbers every time because it's only you taking one number and everything else is multiplied by 0. But it will be slightly smaller because we kind of lost stuff at the edges. So this is on an example of a really big picture. Now, it turns out if you use something like an 8 in the middle and a bunch of -1s, the values in your resulting image, the resulting output, will be phone call, will be large in some places and small in another. And the way this kernel is set up is if all of the pixels in one area have the same value, the value from the output will be 0. But if there's large differences in the pixel values in the area, then there'll be a large difference and you'll get a larger value in your output. And so this kernel generally finds edges. Edges and images are places where the colors change. If you have a region with the exact same set of colors, you generally will get a dark output or a near 0 output in your output image from this convolution. But if there's a large difference, you'll get a high value. And there's other ones too. There's ones called Sharpen and Box Blur. If you've ever done stuff with images before, like edited images, you've probably seen those kind of operations. I don't want to worry too much about them. In general, though, people don't hard code kernel values. This was something we did way back in like the 90s. And this was kind of the state of the art then of how to use images. We used kernels to find edges or kind of find low-level features about images. But in general, the power of convolutional neural networks is that they learn what kernel values are useful for the prediction task. So part of your task when doing convolutional neural networks, and I've explained what that setup is to learn what kernel values you need to help derive output values that help in prediction later on. And so in general, the things you'll be learning from convolutional neural networks won't necessarily be interpretable like edge detection or sharpen. It will just be whatever numbers it found useful that when it created outputs were then useful later on in the neural network for the prediction task. So we'll find that convolutional networks aren't always interpretable. It's hard to interpret what the kernels they're using might actually be doing. I'll talk in class today about how this kind of learning procedure works, how this fits in with our neural network. In this video, all I want you to be kind of more familiar with is this procedure of a convolution. Take an image and a given kernel, kind of making this output from there. That's what I want us to be familiar with in this video. In lecture, I'll talk about how do we apply this in a neural network. Now, one last thing I want to address before we head out is there are a couple other things that you might have been worried about with our convolution, which is, well, what about the edges? Like, what do I do about that? It kind of reduces the size of the image each time. So it turns out there are lots of things you can specify about a kernel, namely How big do you want your kernel to be? In all of my examples, I've been showing you 3x3 kernels. There's no need for that. You could do a 2x2 or a 10x10. It doesn't even need to be square. It usually is square though, but you can make them rectangles. Also, which values you put inside the kernels. That's a thing you have to decide in general as you're using learning for that. It turns out there's other things that people usually use that are useful in kernels. We sometimes think about padding, which is put imaginary pixels outside the image so that you can grab more stuff near the edges. So what I'm doing here is I've actually surrounded my input image that's in blue with a bunch of zeros. So I've put padding of one row and one column that lets us start further at the top of the image so we can gather more pieces from this. See what I mean? Like from this image, we kind of made a new, larger image, which allows us in sometimes more spaces to store our results so we can get more values. So how big you want that padding to be is another choice you could make. Which values you put in the padding is also another choice. Should you put zeros? Or should you somehow try to infer something from the image? Additionally, another thing that people generally consider is what we call stride. So what I've shown you is always make one step to the right, or when you ran out of stuff, ran back to the left and made one step down. We generally also can specify how far you want to jump each time. So this animation I'm showing you below is showing a 5x5 image with a 3x3 kernel, but we've added 1x1 padding of zeros, and we're using 2x2 stride. What I mean is that each time you jump to the right 2, and whenever you have to jump down, you jump down 2. You could change that stride value to be something else if you were interested in doing so. Maybe you didn't want to jump 2 at a time. Maybe you want to jump 1 at a time, like I showed in my earlier example. That's totally fine. These are all hyperparameters you choose. So we'll talk a little bit about kind of what these are doing and how this applies in the convolutional neural network setting in class today. So really big ideas is just what is a convolution, applying this kernel in this window-like fashion across, and some other things you have to decide about it, namely how big your kernel might want to be, what's your padding size and what values you use there, and what stride you have. And in class today, we'll talk about how this applies to a neural network.